guys, today we're going to learn a little bit more about non-blocking assignments. We said as a rule that every time that you use a sequential always block, we should use a non-blocking assignment. Today we're going to explain the why, and we're going to show what happens when you have two flip-flops in cascade. So this will help you understand the physical limits of the digital circuits, and this will also be useful to explain the mechanics of the non-blocking assignment and why it's so important when you are developing sequential circuits. Hope you guys enjoyed. And the input of the flip-flop 2 is connected to the output of the flip-flop 1, and both flip-flops are going to sample their inputs in the same clock. Okay, here the clocks are the same. The clock of the flip-flop 1 and the clock of flip-flop 2 are connected. Okay, so let's try to take a look on what happens only in this guy here. Okay, the input is always set to 1. Okay, in the rising edge of the clock, the input will be sampled. Okay, and after a finite amount of time, the output of the flip-flop 1 will go high. Okay, but notice that it's not immediately. Okay, you have here the rising clock, and the output will go high after a TP propagation time delay. Okay, now let's take a look what would happen in the flip-flop 2. At the same moment, flip-flop 2 will sample its input as well, but at this time, you see, in this case, at this exact same moment, the output of the flip-flop 1 is still at 0. So what will happen here, this guy, in the first rising edge of the clock, it will start at 0. Okay? Now let's see what will happen in the second rising clock edge. Okay? At this moment here, the output of the flip-flop 1 is already high. Okay, and at this moment in the second rising clock edge, the 1 here will be detected by the flip-flop 2, and the output of the Q2, the flip-flop 2, will be high. So what you have here is a kind of delay circuit. The input will be delayed by one clock edge. Okay, if you have here 10 flip-flops, you're going to have a delay of 10, and that's it. Okay, this whole point was just to explain to you guys that there is a physical limit on the device. The physical limit is this: the flip-flop will read then write at different times. Okay, he is not going to read and write at the exactly same time. There is always a propagation delay, and this is what we're going to see now. If we try to write a Verilog code to this using non-blocking assignments, this will explain how the non-blocking assignment works, and we're going to switch it out to the lab and to do some simulation to show how it works. The rising edge of our clock, we're going to sample, we're going to read all the right hand part of our expressions. Okay, so we start our initial state of our flip-flops is that Q1 is in 0 and Q2 is also in 0. Okay, so imagine that you are in the first rising edge of our clock. Okay, at this moment here, D1 will be at 1. Okay, and Q1 will be at 0. Remember, the previous state, our flip-flops started in the state 0. Okay, so what will happen? We're going to read all these the right hand side, and in the end we're going to execute all these assignments at the same time. Okay, and what will happen? Q1 will receive 1 and Q2 will receive 0. Okay, because 0 was the previous state that the flip-flop was. Okay, the flip-flop 1 was at the moment of this rising edge of the clock. Okay, you guys need to take a lot of attention to this, because this is a major source of bugs. Because if you are used to a normal sequential language like C++, Python, MATLAB, whatever, you're going to think that Q1 will receive D1 and Q2 will receive D1 as well, because Q1 got D1. But this is not how it happens in a hardware description language, guys. Here, what you're doing is Q2 will receive the previous state of Q1, not this assignment here that is going to be executed, that's going to be postponed to be executed in the end of this always block. Okay? I'm going to switch to the lab. I'm going to create those flip-flops and going to connect them, and you're going to simulate to see, to confirm what we are saying here. Okay, guys? If you guys have any questions, and this is one of the points that create a lot of doubts in the beginning, please let me know. Before we continue, let's take a look on a very common pattern of mistakes that you may have while developing some stuff in Verilog. Okay? Let's call this pattern the crazy if. Okay? Here in this code, imagine that we reset before our flip-flop states to 0. Okay? And we're going to analyze this piece of code rising clock edge by rising clock edge. Okay? So, imagine that we fall in this part here of the code, okay, in the first rising edge of the clock. In this first rising edge of the clock, as the reset has been applied before, Q1 will be 0 and Q2 will be 0. Okay? And we execute this line here. Q1 receives Q1 plus 1. And if Q1 bigger than 0, Q2 receives 1. Okay? The problem that you may find here is this, guys. When you are dealing with a normal programming language, you may think that here Q1 will receive 1 immediately before this line executes. But this is not what's going to happen. Here, in the first rising edge of the clock, Q1 will be 0, okay? He will receive 1 after this whole always block execute. So what will happen here? Q1 will receive 1, and this if here will not execute. Okay? This if will execute only in the second rising edge of the clock. Okay? Which means Q1 will be updated only in the end of the always block. So this if will only be available in this moment here, in the second rising edge of the clock. Okay? And Q2 will have the value of 1 in the third rising edge of the clock. Okay? This is something also that, for instance, imagine that you put another if here. If Q2 equals 1, this will not execute as well in the second rising edge of the clock. Okay? So, as a rule of thumb, avoid to create a lot of complex ifs and a lot of complex logic in a sequential always block. Okay? In the future, we're going to see how to do state machines, and this is the way to create more more complicated logic in digital designs. Okay? Okay, guys. Just to remember a little bit, let's take a look on the general flip-flop D. Here I'm trying to simulate the circuit in a program called Multisim. Is where you is a nice program that lets you simulate electronic circuits, analog and digital. And let's just play the simulation, and you can see that what happens is that in the rising edge of the clock there is a time, there is a propagation delay that the output is going to go too high. Okay, actually we sample really fast, but it takes a little bit of time to create the output. Okay, and this is just to show the effect. Now I'm going to take out the generator and simulate by hand, like pressing space, and you can see the delay effect of cascading two flip-flops. Okay, now let's change to the Vivado, and let's create this design where we have two flip-flops in cascade, and let's simulate to see more or less what we're talking about. Okay, so how we showed before in the board, we have an always block that is going to execute in the rising edge of the clock, and we reset the states if the reset pin is high, and if the reset is not high and we are in the rising edge of the clock, we're going to assign the some input D to the first flip-flop, and the second flip-flop will be cascaded to see the output of the first flip-flop. So, so these will exercise nicely what we want to show here, and will help you also to understand what happens in the non-blocking assignment. So just to remember what will happen. In the moment that we have the rising edge of the clock, the right hand side of the expressions are going to be evaluated, okay? And in the end of the whole block, the whole always block, in the end of this begin, we're going to update our signals, but with the values that we sampled before, okay? Okay, now I'm just showing the schematic of those two flip-flops in cascade, and we're going to create later a simulation to see this. Now, creating our test bench, just following the same recipe of a sequential circuit test bench, where the inputs we declare as reg and the outputs as wires, and there we instantiate our block, create our clock, and then we add some initial values for the inputs, and then we add another initial block to stimulate our device under test. Okay, nothing fancy, nothing changes here. Okay, now we instantiated. I put on the left this recipe, and this same pattern you're going to see a lot, so it's nice to take note. So basically what we're going to do, we generate our clock, and our stimulus is quite simple. We just do a reset, okay? And after the reset, we still on the falling edge, we add some value like 1 at the input D, and we wait for 2 cycles. And you're going to see on the simulation that after 2 cycles, the input at D will be propagated to the output of the second flip-flop. And this is exactly what happens if you cascade flip-flops. You create a unity delay, where every flip-flop will be one clock delay. By the way, when we see filters, this will be quite useful as well. So, in the simulation, you see that the D input will only appear in the second flip-flop like 2 cycles after. Okay? And just take a look a little bit more in the test bench to understand more. But basically it's this, we can finish the video. and hope you guys like it. And if you have any doubts, just put as comment, and I'll try my best to help you guys out. Okay?